Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and I'm going to talk a little bit about how heat is distributed vertically in the atmosphere and how the process of convection actually aids in that process. And I'm going to be showing you a chart which I've showed you before, unless you're a new subscriber, and it's called a skew T chart. And we'll talk a little bit more in detail about what we can do with that. So let's go on ahead and cornerize myself here. And this is a bar graph of the temperatures at Greensboro yesterday. Now, why am I picking Greensboro and why am I talking about yesterday? Well, you all remember that Monday night was the clear, calm night where some areas saw some pockets of frost on Tuesday morning. And so I wanted to talk about a day where it's clear and calm and the air is dry and it's very chilly in the morning, and then the sun goes to work and warms things up significantly during the day, and there's no change of air mass. Okay, the only changes in temperature are a result of sunshine. So you look at this graph here, at 7 a.m. it was 38, and then it jumped 7 degrees to 45, 7 more to 52, then 5 to 57, 4 to 61, and then 2 to 63, 2 to 65, 2 to 67, 2 to 69, 1 to 70, and there was no increase at all between 4 and 5. So you notice the temperature rose most rapidly right after sunrise, and then that rate of increase dropped off as we headed on into the afternoon. Here's another way of looking at it graphically. This is the number of degrees that the temperature went up during these hour-long periods. So we had a 7-degree jump from 7 to 8 and 8 to 9, and then it dropped to 5, and then 4, and then 4 consecutive hours of 2, and 1 hour where it was only 1 degree, and there's no bar on 4 to 5 because the temperature did not change. So why is that? Why do we have a rapid increase in temperature to start and then it levels off as we head into the afternoon? So we're going to be talking about how heat is distributed vertically in the atmosphere, and this is what we call a skew T log P chart. Okay, now it's called skew T because the lines of constant temperature are skewed or at an angle, and the reason it's called a log P chart is that mass in the atmosphere is actually distributed logarithmically, where most of the mass collapses near the surface of the Earth, and then as you go higher and higher up in the atmosphere, the decrease in mass is not nearly as quick. So for instance, if you go from 1,000 millibars to 850 millibars, you lose 150 millibars of pressure over about 4,500 to 5,000 feet. But to get that same decrease in pressure way up in the atmosphere, you might have to, go 10, 15, 20,000 feet, to be able to get that kind of a drop. So the atmosphere is much more dense near the ground than it is higher up. So the lines that are straight across, okay, are lines of equal pressure. You can call them isobars, okay? It's just we're looking at it a little differently here because instead of looking down with 2 dimensions, we're looking up with the third. So the lines that go this way, okay, are the ones of equal pressure. Now, the lines that are skewed at an angle, like these here, are lines of constant temperature, or isotherms, if you will. And then finally, the lines that go like this, and these lines are actually not perfectly straight, but it was close enough for this example. So these lines are called dry adiabats. And you've all probably heard people or me talk about the dry adiabatic lapse rate, where if the air is well mixed, the temperature decreases at a rate of about 5.5 degrees per 1,000 feet. And so if the atmosphere is well mixed, then that means that the temperature would be decreasing right along this line here. Okay, so if lines of constant temperature are this way, and you're traveling along a dry adiabat, then you're almost perpendicular to those temperature lines, and so the temperature is definitely decreasing with height. So here is our skew T log P chart. This is just a hypothetical here, okay? So the green area, we're going to say the surface is right at 1,000 millibars, okay? And the temperature is, I think I put that at about 40 or 41, and we have an inversion where the temperature actually increases with height, gets up to about 50 at about 960 millibars, and then it decreases dry adiabatically above that, okay? Now, the way that this chart would change if you were actually taking a look at it every hour, if they were sending up a weather balloon every hour, this is what would happen, is that the first part of that inversion gets knocked out, okay? So now we have a dry adiabatic lapse rate over this very thin layer, and then our inversion is here, and then the rest of it is unchanged. Then we knock out a little bit more of that inversion, okay? So now we've got a dry adiabatic lapse rate over a deeper layer, still got a little bit of an inversion in here, and then finally, when the sun is strong enough to knock out the entire inversion, then we have a dry adiabatic lapse rate all the way from the ground up to whatever height the atmosphere is well mixed. Okay, so this was Greensboro, North Carolina on Tuesday morning. This is the actual data from the weather balloon that was sent up. And so their temperature, again, was just slightly below 40. At the surface. Their surface pressure was actually, I think, 990 millibars. And then it went up like this. This is very similar to the hypothetical case I just showed you. And then the temperature begins to decrease, not at the dry adiabatic lapse rate, but certainly, here it's increasing with height and here it's decreasing. Now, by the time we got to the evening, when they sent up the weather balloon at 8 o'clock, the inversion's gone, okay? We're basically dry adiabatic all the way from the surface up to about 830 millibars, and then you have the inversion here, much like you have here in the morning. Now, do you see these little, what I call parallelograms, okay? Like for instance, let's take this one in here. You see this little four-sided figure there? And that is created by the lines of equal temperature and also the lines of constant pressure. Those little parallelograms, if you will, are called solenoids, and basically the amount of energy required to heat the air is proportional to the number of those little solenoids, okay? So let's take a look at what would happen first on a day like this. So by the time we got to about, 10 o'clock, maybe 11 o'clock at the latest, this is what the sounding probably looked like, where we got rid of the inversion and we're now dry adiabatic from like 940 millibars down to the surface. So if you were to be able to count, okay, exactly how many of those little parallelograms exist, this is the amount of energy that would be required from the sun to knock out that inversion. And if I just roughly look at this here, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe another 4, 18, 21, maybe 22, 23, somewhere in there, okay? Now, in order to get the sounding over to here, which is where it was at the end of the day, the sun now has to knock out this entire area, like between this line, this line, this line, and this line, okay? And there's way more than 22 of these in this entire area here, okay? So once you knock out that inversion, then the atmosphere has to, in order for it to go up 1 degree at the surface, it's got to make the entire sounding, if you will, go up 1 degree, which means that it's going to have to do that all the way from the ground up to above 850 millibars, okay, or about 5,000 feet or so. And so this is the reason when you have a chilly night, a clear, calm night where the coldest air is right at the ground, and then you impose sunshine, you have a perfectly sunny day the next day, and there's no change in air mass, no fronts coming through or anything, that it's going to knock out that inversion pretty quickly because it doesn't require that much energy to do that. But once the atmosphere becomes well mixed over a great depth of several thousand feet, then it's got to heat that entire layer, okay, before the surface temperature can go up any more than 1 degree. It's got to heat that whole layer 1 degree, and then the next layer, which is probably deeper, another degree, and the next layer, which is probably deeper, another degree above that. So that's the reason why the increase in temperature slows down, because it requires more energy to make the temperature go up, because it's got to heat an entire layer, which is much, much deeper than the layer that inversion existed across, okay? Does that make any sense, okay? And again, this is only true on a clear, calm, cold night, and then you have a complete day of sunshine the next day. And this is how the sounding, or what the radiosonde finds when it's launched from a given location. This is what it would find: is that we start off with temperature increasing with height and then decreasing with height. We get rid of the inversion, which doesn't require much energy at all. And then we've got to, for every degree that we heat the surface, we got to heat this entire layer all the way up to here, and the temperature rate increase, or the rate of increase, slows down considerably. Okay, that was my best shot at explaining that. That is the bonus weather video for this Wednesday. The next one will be coming up on Friday. Next daily weather update coming up tomorrow. And I hope you have a wonderful Wednesday evening. And I hope this doesn't skew your evening too much. And if it was cold, I'd ask you to put a log on the fire, but it's probably not cold enough to do that. Get it? Skew, log. All right. See you tomorrow. Take care.